Welcome to Engineering Design and Development, a capstone course where two classes go head-to-head in a robotics challenge designed by the CARPA Initiative. The student teams form two unique companies in which they collaborate throughout the year to develop innovative solutions and compete in a final showcase. Our company, Astraea Industries, is composed of 10 technical and non-technical sub-teams, all working together to bring our vision to life.
For the 2025 CARPA Initiative project, The Flight of the Phoenix, we are tasked to design and build a dual rocket and aerial drone system. Our mission begins with the launch of a rocket that must climb between 100 and 400 feet. If the flight is disrupted by the opposing team's turret, our system will record key flight data and prepare for drone for separation. The drone then unlatches, transforming to safely deposit the primary booster, locate a secondary launch platform, and attach itself as the nose cone to the secondary rocket booster for the relaunch of the second rocket stage. The system then ensures a precise landing within a 10-foot radius, successfully completing the mission.
Our design is pretty simple if we abstract it. After all, it's only a drone that's mounted using electromagnets to a model rocket. But once we start going deeper into it, a lot of challenges do start to surface. A lot of the major issues that we've had were actually surprisingly with the regulations that we've been facing. For example, to keep this rocket and drone system legal, it has to weigh less than 1,500 grams. But achieving that limit while having all the components that we need, for example, a GPS, a cone on top of the drone to make sure it flies straight, and even a big enough rocket motor to lift the system off. All of these have added substantial weight. And so this legal issue has been a major issue that we've been trying to work through, more so than the actual design elements at play. Another thing that we're working on is making sure that the drone arms are secure when they're able to fold. The drone is required to fold into a cone-shaped position so that we are able to fly using the rocket in a pretty stable fashion. But in order to achieve this folding, we've had to try different solutions because we weren't able to quite get it just right. Currently, we've added clips to the top of our drone that physically secure in the arms when they fold up. And so just as we were going through the process of designing our system, things popped up that we weren't exactly prepared for them in the beginning. And honestly, that's something that has made this class pretty interesting and really refreshing, because you never know what you're going to have to encounter, what you're going to have to change about your design. And so at this point, we're in the beginning part of May, and the launch date is coming up soon. But MEC is pretty confident that our system is designed to meet the specifications that were outlined. And so now we're handing it off to Prague and Electrical, and here to support them and give them our all.
For this year's drones, functions and programming, the main consideration was how we would be able to fulfill all the tasks assigned by the CARPA Initiative. And so the main two that we were immediately able to identify was that we would need a functioning drone that could function as the nose cone of a rocket without affecting its flight course. And we would also need some type of robotic vision vision software that would allow us to detect where we needed to drop off the primary rocket body and then where we would need to land the secondary rocket body. So in order to accomplish these things, for the drone specifically, we use a program called Q Ground Control, and it's essentially a software that allows us to facilitate the communication between our drone and a remote controller. And so we decided to go down this route to ensure that the drone worked properly before we moved on to autonomous testing. And then additionally, we were also working on a vision program using a Raspberry Pi, which is a type of basically a mini computer, as well as a Raspberry Pi camera. And so these two things in combination allowed us to gather a stream of video feed and then detect markers on the ground called April tags. And with these markers and OpenCV, which is the software that we decided to use, we were able to do something called pose estimation, which was find how far the tag is in relation to the camera. And so using that data, we were then able to command the drone to move towards the targeted tag. For autonomous testing, the biggest issue was ensuring safety, because obviously when we're doing it manually, we always have control over the drone. We have kill switches and we're able to control how the drone flies, but if we rely solely on autonomous programming, we have much less control. And so we were able to mitigate this by trying it in simulations first and then trying it without propellers first in order to ensure that it worked properly.
During our development for the Thunderbird drone system, we had a lot of issues, and it was a very iterative process that we had to make a lot of iterations for. First of all, we had a lot of issues with the space within our drone to store the electrical components. So we had CAD design and give us more space within the drone, and we also worked with CAD to make sure that our configuration of the electrical components was maximizing our space. And another issue that we came upon was the weight of the drone, and so we initially had 2 buck converters powering a Raspberry Pi and our Arduino, which would be used for our EMASH testing. But after our POC presentation, we decided that we actually didn't need those buck converters, and we could actually power our Raspberry Pi straight from the PDB. And we also decided to get rid of our Arduino because we realized that we didn't need air brakes, and we were under the 400-foot rocket limit, and so we decided to get rid of the buck converters altogether and the Arduino altogether. And beyond that, to navigate these changes, we just made sure to do as much prep work as possible, so once our design was getting finalized, that we could get straight into the electrical work.
The Engineering Design and Development course also offers a student intern program, where students in grades 9 through 12 have the opportunity to gain hands-on engineering experience. The interns are thoughtfully selected through an interview process, where the directors and members of both student teams question and review possible candidates. Our selected interns work to support our different sub-teams and learn valuable skills alongside Astraea's team members.
This year, the interns were tasked with making the launch tower and the turret for the project. It is to aid with the launch of the drone and the rocket body on the actual project. And as for the interns joining our team this year, it is to help them be readily prepared and implementing the engineering design process so that they are ready when they are taking the EDD class as seniors for their capstone project. And as for current progress, they have finished the turret and is currently undergoing testing, and they have pivoted from making two launch towers to one launch tower. So we are currently writing up a proposal and investigating how to do that.
Hello, I'm Neil Marquez. I'm part of the Impulse Consulting team, and my role is to help Astraea with their rocketry-related questions. So we've performed several tests in Lucerne Valley and El Mirage Dry Lake to test the stability of the rocket, and this is to prepare the rocket for its final purpose, which is to have a drone attached. So we need to make sure that the rocket itself is stable before we test it with the actual expensive drone equipment.
3, 2, 1.
This role has been really rewarding to me because I've found that seeing the team learn about rocketry has really inspired me to keep going in my own rocketry pursuits as well.
From working with Astraea, I learned how to operate in a fast work-paced environment, where changes happen constantly. This experience helped me navigate similar situations in the future, where instead of fumbling, I can adjust to the situation at ease.
I'd say my biggest takeaway from EDD this year was learning to work effectively in a professional environment. It was definitely difficult managing a year's worth of tasks and coordinating work between departments, but I learned a lot about organization in the process. I became more comfortable with Microsoft Teams, the Agile system, and just communication and organization in general. Learning such real-world skills with Astraea will definitely make the adjustment to a professional environment in my future career easier, and I'm forever grateful for my time in EDD.
Here at Astraea Industries, we've gained a newfound understanding of not only rocketry and engineering, but also the fundamentals of collaboration and perseverance. Together, we've turned ambitious ideas into tangible progress, proving what's possible when passion meets purpose. On behalf of Astraea Industries, we'd like to thank the CARPA Initiative, industry professionals, expert advisors, and our donors for supporting us and guiding our team through this mission. This is just the beginning, and we're ready to reach even greater heights.